Good morning, everybody. It's my absolute pleasure and privilege indeed to invite and also introduce Professor George Mashour, MD, PhD. He's an anesthesiologist and NIH-funded neuroscientist at the University of Michigan. He's internationally recognized for his work on consciousness and the mechanisms of unconsciousness. Mashour was the founding director of the Center for Consciousness Science at the University of Michigan, where he currently serves as the Robert B. Sweet Professor and Chair of the Department of Anesthesiology. He's also founded the Center for Drug Repurposing, I believe in 2019, and serves as co-director of the Michigan Institute for Clinical and Health Research. Mashour serves as a member of the NIH Surgery Anesthesiology Trauma Study Section, as a trustee of the International Anesthesia Research Society, and as president-elect of the Association of University Anesthesiologists. After his undergraduate study of philosophy, he received his MD and PhD in neuroscience from Georgetown University. He was an intern, resident, and chief resident in anesthesiology at the Massachusetts General Hospital and Harvard Medical School. Mashour has received numerous institutional and national awards throughout his career, including 2 Fulbright scholarships, the Presidential Scholar Award from the American Society of Anesthesiologists, and election to the National Academy of Medicine. Congratulations, George, on that achievements, and looking forward for your talk. Thank you so much, and take it away.
Well, thank you, Bala, and thank you all for joining. I really appreciate the invitation, and I think it's fantastic that you are also leading the way in terms of consciousness, and I think with a broader view even than we have here at the University of Michigan. So I think that's wonderful. Just in terms of disclosures, really none for this particular talk. I am a consultant for TRIP Therapeutics. Really, it's about a future project, has nothing to do with this research. And one more caveat, I focused on some older research. This isn't necessarily about the very current work that's going on in our laboratory, but given the focus of your center on consciousness and also aspects of spirituality, I just thought this particular topic, even though it's not as fresh in terms of our research program, would still be of real interest to discuss, and is certainly still a topic of lively discussion. So I'm going to talk about consciousness and the dying brain. I'm going to start off with some basics on the neurobiology of consciousness, really just a very focused introduction to a few key concepts within a certain theoretical framework. I'm then going to move on to talk about the phenomenology of near-death experiences and also a bit of the epidemiology. And then finally combine those two with a description of a study on the neurobiology of the dying brain. So I'll start off with the neurobiology of consciousness. And essentially what I would like to claim, and this is a matter of heated debate, obviously, the nature of consciousness, the neural correlates of consciousness, but I think there is evidence that consciousness is not correlated exclusively with primary sensory processing, that there appears to be something that's required beyond the level of the primary sensory cortex. This is an older neuroimaging study with an auditory paradigm, and essentially you can see activation of the posterior half of the superior temporal gyrus, which is the site of the primary auditory cortex, even with a non-detected sound, whereas the detected sound has a much wider spread activation, notably in the frontal and posterior parietal cortex. That's a study of the auditory modality. This is a study of the visual modality, and it's an electrophysiological study. And you can see the schematic representation on top, and down here at the bottom, essentially evoked potentials. These are visual evoked potentials. And what these authors found is that conscious processing appeared to be better correlated, again, with a wider spread activity, longer latency evoked potentials that are presumably happening beyond the level of the primary sensory cortex. And importantly, especially in the context of this particular talk, not only is there this traditional feed-forward pathway going from the primary visual cortex in V1, heading anteriorly, but there is also feedback connectivity. And this comes up with a lot of different terms in the literature: reentrant processing, reverberant processing, reafferent processing, feedback processing. But the basic idea is the same, which is that assuming a neurocognitive hierarchy, that higher order areas receive information and then feedback to more primary areas. And lest you think that I'm stuck in the literature of 2007, this is an article from 2018, also a visual study, but in the non-human primate brain, where they were recording from primary visual cortex, V1, higher order visual cortex, V4, and also the dorsolateral prefrontal cortex. And again, what they found is that consciousness, a particular form of consciousness, was associated with this widespread activation, and again, with the feedback mechanism. And this reverberant activity across the feed-forward and feedback processing is ignited, if you will, by the prefrontal cortex. Now, there are actually some parallels, or anti-parallels, I guess, in anesthesiology. And this was one of the first studies to demonstrate that cortical feedback is selectively disrupted in rats. So I just showed you a representation of empirical data on top, but then some modeling on the bottom, suggesting that this feedback processing is important for consciousness. It helps sustain and amplify and make accessible sensory representations. And what my colleague Tony Hudetz, who's now here at the University of Michigan, demonstrated is that if you administer a commonly used anesthetic, isoflurane, in rats, that you will selectively suppress that feedback activity. So this is a schematic of a rat brain. This is the frontal cortex, the occipital, the parietal, and these arrows represent a certain measure of directed connectivity called transfer entropy. In this case, higher frequency activity. And these animals had visual stimuli. So these are visual evoked potentials. And in the awake state, again, you can see this feed forward in green and the feedback in red. But look what happens after induction of anesthesia with isoflurane. In the schematic representation, the feed forward activity persists, but the feedback activity is selectively suppressed. Now, if you increase the vapor concentration, you're going to have a more global suppression of connectivity, but at concentrations consistent with anesthetic-induced unconsciousness, this feedback connectivity is selectively suppressed. And what I did earlier on in my career is to demonstrate that this can be shown in humans and also shown across a diverse array of anesthetics. So again, right here on the y-axis, you have symbolic transfer entropy. It's a cousin to transfer entropy, which I showed in the last slide. This is time on the x-axis. And the trace in red is feedback from frontal to more posterior brain areas. The blue is feed forward. The gray shaded area is when the drug is being administered. And what you can see pretty clearly, just in qualitative terms, is that the feedback connectivity is suppressed after and during administration of all three of these anesthetics, despite the fact that ketamine is, molecularly at the neuroscience, systems neuroscience level, just a very distinct drug, distinct pharmacologically, distinct neurophysiologically, and yet, despite all those distinctions, there's a very consistent behavior. And this was later demonstrated in a more detailed way. Now we're going back on the translational spectrum to non-human primates. The study was published in 2018, a study of dynamic fMRI connectivity. And again, you don't need to be an expert in any of this to see that there are rich interactions in the awake state that get suppressed during ketamine, during propofol, and also during sevoflurane. And all of this is consistent with what's referred to as the global neuronal workspace theory of consciousness, which is that consciousness really emerges from the interaction of many different sites, normally unconscious cognitive processors that gain access in this process called broadcasting to a sensory representation. But for the purposes of this particular study, I just want to suggest that consciousness is not correlated with activity at the level of the primary sensory cortex, but it does appear to correlate with activity and feedback connectivity in these frontoparietal networks. And I've shown you some data from human studies as well as animal studies, both in terms of content of consciousness and also level of consciousness with anesthesia. And this point is going to be important to give you context for what we're going to see later in the talk. So now I'd like to move from the neurobiology of consciousness to the phenomenology and epidemiology of near-death experiences. So near-death experiences have been reported since antiquity. They have a very similar description. This actually is a Bosch painting from the Middle Ages. And again, some differences, but consistent description of an awareness of being dead. Typically, this is a peaceful experience. Sometimes it's dysphoric. There's often an out-of-body sensation, a sense that you're floating or drifting through a tunnel. And of course, that's a common representation of the tunnel with a golden light. Often communicating with a presence or specifically a deceased relative. This is, again, typically a very positive experience and also associated with life recall. That the phrase, my life flashed before my eyes, but that recapitulation of many or key life events. Now, in the early 2000s, there were actually some formal studies related to the epidemiology of near-death experiences. Now, these near-death experiences can happen in many different settings. They can happen drowning, with comatose states. Sometimes they can happen even in the absence of death or a threat of, well, actually they happen in an absence of clinical death, but are evoked by the threat of death. So somebody who's in a car accident might have, even though they're clinically intact, might have a near-death experience. Sometimes those are referred to as fear-death experiences because they're evoked by the fear of death. But in order to study this systematically, you need a more controlled setting. And so the setting that was chosen by Pim van Lommel and Sam Parnia were cardiac arrest survivors in the hospital. And so there was a major study published in The Lancet in 2001, and then also a smaller study published in Resuscitation also in 2001, and there was a follow-up study that I'll note later. But in terms of these initial epidemiology studies, what Van Lommel and colleagues demonstrated is that 344 patients, 509 successful resuscitations. They used a more liberal scale for near-death experiences that had been published in 1980, and they found that 18% of these cardiac arrest survivors had a near-death experience. Now, that's a pretty striking number. I presume we have some residents on the call and, well, faculty. I mean, we've been at these codes, right? We've been at these codes. I mean, can you imagine, that 1 in 5 or even 1 in 10 of the patients that you're resuscitating during a cardiac arrest are actually having this kind of profound conscious experience? It's pretty striking to hear this. And importantly, there was no difference in pharmacology. It didn't appear as if resuscitation with certain drugs evoked these near-death experiences versus other drugs. The Parnia study published in Resuscitation had a smaller number of patients. The number of successful resuscitations were unknown. They used a more conservative scale published by Bruce Grayson, who is really very involved in this field and has made a lot of contributions. In this study, there was a lower incidence, 6.3% had near-death experiences. Again, there didn't appear to be any difference in pharmacology. And I just wanted to highlight, those were kind of the original seminal studies in terms of the epidemiology, but in this case, this was more recent, 2014, it was much bigger, again, led by Sam Parnia, who's done a lot of work in this field, and also just in the field of resuscitation in general. And they demonstrated an incidence of about 9%. So again, it's something that's consistent. 1 in 10 to 1 in 5, as far as I'm concerned, is very striking when you consider the number of cardiac arrests that we're experiencing in the hospital here or at Beth Israel. I also want to note that these experiences are transformative, and this was more formally studied by Pim van Lommel with 2-year outcomes of cardiac arrest and comparing those who had a cardiac arrest with or without a near-death experience. So the cohort here is a group of individuals that all had a cardiac arrest. The so-called life change inventory questionnaire, so social attitude. There were significant differences in showing feelings, accepting others, being more loving and empathetic, being more understanding, changes in religious attitudes, a greater sense of purpose of life, sensing the inner meaning of life, interest in spirituality, not necessarily an interest in organized religion per se, to be clear. And then also some other factors related to the attitude toward death, reduced fear of death, belief in life after death. So a single experience had really a transformative effect, almost to the point, for many people where they have a hard time reintegrating into their normal lives. They have such a transformation of values that it's difficult to go back to their old set of values and the old set of relationships prior to the near-death experience. So, to summarize this portion of the talk, a significant proportion of cardiac arrest survivors report near-death experiences. They appear to be independent of pharmacology, and the near-death experiences can be transformative. So now I want to move into this final portion of the talk that looks at the interfaces of the neurobiology of consciousness and, if not near-death experiences, then near-death states. And I'm going to start with some case reports in humans that come from the critical care setting and the operating room setting. And what was observed by Chawla et al. And Aoyang et al. Is that at the time of death, either during donation after cardiac death, or this was a critical care patients, that there was a surge of electrical activity in the brain as detected by the EEG, in particular by the bispectral index monitor. And I'm sure that many of you are familiar with this. This is a long-standing monitor. Takes a frontal EEG montage, and there's certain parameters and subparameters, and it's processed, and then an index is reported by the monitor. This is an old version. That ranges between 0, which is isoelectric activity, and 100 being awake. And as you likely recall, this is more of a sedative state, and really 40 to 60 is the range of general anesthesia. And I would also note that when we've done large studies of the bispectral index, and I'm not going to discuss them here, but when you're delivering a garden variety everyday anesthetic and you have a BIS on, even if you're not aware of the BIS, you're hovering at around 43. So, a general anesthetic as we know it is typically in the low 40s. And I just want to show you some examples now with that context of these surges in the dying brain. So this is one patient. So you've got time here on the x-axis and the BIS value on the y-axis. Remember, 0 is isoelectric, 100 is awake. So this individual is at maybe high 70s, and is cruising along here in the high 70s. It's more of a sedative range or somnolent range. Maybe they had pharmacologic sedation. And then you can see this going down. So the patient is dead here. You can see them going down, and then before the point of death, there's the surge that occurs. And then it goes back down to zero. This is an even more striking example, I think, of an individual who's really in the range of general anesthesia, 40 to 60, actually dipping down into a range that would be consistent with burst suppression and deep anesthesia. And then look what happens. There's a little spike here, and then this individual is going up to 100 before it drops off to zero when they die. And so these cases were very provocative in terms of a potential neural mechanism for near-death experiences, a final surge in brain activation. And I think many of us who have seen dying patients, if we don't have an EEG on, we've seen sympathetic surge. You see changes during this dying process. But of course, there are some key difficulties of interpretation. First of all, the patients died. So we have no idea what the experiential content was during that period of the surging electrical brain activity. The other thing is the surge just might reflect a nonspecific activation. You've got neurons that are dying from hypoxia, they're spilling glutamate, and then you're getting into this excitotoxic zone where you've got widespread activation, could be having a seizure. I mean, there are different reasons why there could be activation that really don't have anything to do with consciousness. And then, of course, there are also limitations of the BIS monitor and truly reflecting conscious experience. That's a whole other lecture, but suffice it to say, so even independently of the BIS, just having a pure frontal montage, there are going to be limitations in terms of what you're going to be able to say about conscious processing. And so this is what motivated us to conduct a study on the neurophysiology of the dying brain. And I want to give a lot of credit to Dr. Jima Borjigan, who's a physiologist here at the University of Michigan. And she came to me in 2012 and asked, can we use a BIS monitor in a rat? So, well, why would you want to do that? And she told me about some observations she had had. She and her husband, Michael Wong, study stroke. They do neurochemistry, and they saw some neurochemical surges, in rats that had died overnight when they went back to look at the HPLC record. And she was wondering, could this be connected to the near-death experience? So I said, well, this is fascinating, but we wouldn't want to use a bispectral index. We can't in a rat. I don't even think we want to use the parameters, but we have a whole suite of analytic techniques that we're using and exploring in humans that we actually can use in these rodents. And that connection with someone who just happened to have a lab down the hall and knew about our work and awareness in the bispectral index led to this paper about 14 months later. So this was a very intense collaboration that resulted in this. And here's the methodology. It's really a very straightforward study. We had 9 rats, and they were implanted with bilateral frontal, parietal, and occipital EEG. There was also EMG and EKG electrodes placed, EMG electromyography, and of course, EKG electrodes. And then we recorded this electrophysiology during the waking state and also during general anesthesia with ketamine and xylazine. And for those of you who do animal research, you'll recognize this as a very common anesthetic cocktail. For those who don't, xylazine is an alpha-2 agonist, so it's sort of like a dexmedetomidine-like drug, and it's this cocktail with ketamine is commonly used in animal studies. And then we induced death with a direct intracardiac injection of potassium chloride, and then we saw what happened. We analyzed the EEG for spectral power, that is the contribution of particular EEG bandwidths to the overall pattern. Functional connectivity. Functional connectivity, so in different kinds of connectivity in the brain. We have structural connectivity, just the physical connections between one brain area and another. Functional connectivity, which reflects a kind of statistical covariation between two different areas of the brain. So if they're doing similar things in a coordinated way, that perhaps they're jointly working towards some common function. It's an inference. That's not a definitive conclusion. And then directed connectivity. And that's a form of functional connectivity, but it's really trying to get at not the cross-sectional covariation during a particular time point, but rather the influence, or making inferences about the influence of one area of the brain on another over time, okay? And I just showed you some examples of that. Symbolic transfer entropy, that go down when you get general anesthesia, and that feedback connectivity goes down, and that go back up when you recover from anesthesia. So here are the data. So first of all, I want to note that there was a very consistent behavior across all 9 animals. This is a small study, but as my physicist colleague Anshul Lee, who is the co-first author, said, it's almost like I'm looking at the same rat. It's just a consistent pattern. And so I want to direct your attention over here. This is what is referred to as a spectrogram. It's a heat map. And so on the x-axis is time. On the y-axis is the frequency, and then the color, the heat, if you will, reflects the intensity of a certain frequency. So the red colors are hotter, higher. The blue colors are lower, cooler. Now, I want you to look at what I have circled here. So this little dot here, that's when they got the potassium chloride injection. And what you can see here is this hotness at around 40 hertz, and some hotness also in the theta bandwidth. So now let's look at the left side of your screen. In the white box, that's the waking state. Black is anesthesia. Red is in this third phase of cardiac arrest. And the phases or stage really defined by the neurophysiology. So you can see a significant difference in theta power and gamma power. And this is relative power. So it goes down during anesthesia, as we would expect. And note here, delta, the slow wave activity, goes up during anesthesia, as we would expect. Heading back to theta, and then in red, you can see there appears to be a surge. And in the gamma bandwidth, in 40 hertz, there appears to be a big surge. And this is interesting. So this was provocative because, especially because 40 hertz activity in the gamma bandwidth has a long and storied history as being considered a neural correlate of conscious experience, especially when it is coordinated across the brain. And theta activity, let's say around 8 hertz, in animals is typically associated with a state of wakefulness or REM sleep. So an activated cortex with the capacity for associated phenomenology. But, you know, it's just a surge of power. Again, maybe it's just non-specific. But then we also saw that there was a surge of coherence. Now, you're looking at a map again. This is called a spectrogram. This is called a coherogram. It's reflecting these statistical covariations that give an indication, you make an inference, that perhaps these areas are somehow working together or communicating together, or at least have the conditions under which they can communicate. And you can see, you know, again, similar phase, hotness here, also hotness in higher frequency activity, also associated with conscious experience. And again, now I'm giving you a graphical representation of the same data, that in theta, you go down during anesthesia, you go up during cardiac arrest, and similarly in this 40 hertz bandwidth, this big increase in coherence across the brain. All right, so now it's a little bit more provocative, but maybe if you had a seizure, you could also see increased coherence, and that would not be consistent with conscious experience. But this is where things, I believe, got really interesting, and that is what happened with directed connectivity. And this is where now we're moving more to a level, again, can't make definitive statements, but is more suggestive of one area having a meaningful interaction with another, that there is actual communication going on. And what you can see, so remember those feed forward and feedback directions, you can see here with feed forward at the bottom of your screen. Again, the white box is waking, black is anesthesia. That feed forward connectivity goes down, which it can during anesthesia. And then it goes up. And again, gamma goes up. And the same is true for this feedback connectivity. And in the gamma bandwidth, there was an 8-fold increase in this directed transfer entropy. Now, let's think back to the first part of the talk. I showed you empirical data that when rats are anesthetized with isoflurane, they have a suppression of feedback activity actually in the gamma frequency, that study by Tony Huditz. And I've shown you in humans that there's also a suppression of feedback connectivity. So this is re-emerging, and actually re-emerging at higher levels, 8-fold increase over the waking state in the setting of cardiac arrest, okay? So critical questions. I mean, first of all, a critical question, what can we say about consciousness or experience based on an animal study? That's a much wider conversation, but I do have some thoughts on that. But just getting more to the technical aspects. First of all, could this signal be artifact? Now, let's say the brain went flat, but there was still some, let's say, VFib going on, still some residual cardiac activity, maybe not consistent with life, but enough to be detected on an EEG, right? So that was one question I had. Another question we had is, well, maybe this arousal, could that have been due to the pain of the intracardiac injection, right? I mean, we have people under anesthesia, and then they have a surgical insult, and then they can wake up or they can get aroused, right? Was that going on here? So in terms of the signal artifact, what we did to try to assess that is we did a correlation between the muscle activity, the brain activity, the heart activity, the brain activity, the muscle activity, and the heart activity. And that's what you're looking at here, EMG and EEG, EKG and EEG, EMG and EKG. And all of these are centered around 0, suggesting that it's not simply that the EKG activity went in this direction and the EEG followed it. So there was no correlation between these signals. Then the other thing we did to control for this stimulus, arousal, was we had a different mode of death, where instead of doing a potassium injection, we had the animals inhale carbon dioxide. So this was more of a respiratory arrest model. And this is the power. So now you're looking at a spectrogram, and what do we see? A very similar surge in the 40 hertz activity, which you can see here quantitatively in this histogram. Now the theta wasn't statistically significant, but qualitatively a similar pattern. And look at what happened with coherence. Again, this hot red bar around 40 hertz during kind of a similar stage of a hypoxic or respiratory arrest. Also see some of this high frequency activity, 200 to 250 hertz. And I want you to look at it side by side. So on the left side of your screen is the cardiac arrest, and this is the respiratory arrest. And very similar spectral properties, suggesting that what we were seeing with that arousal wasn't merely due to the pain of a needle going into the heart. Now you could consider whether or not, inhaling CO2 would lead to activation. I mean, there are all sorts of things that we can consider. But in terms of basically controlling for the noxious stimulus of the needle, we found a similar behavior. So to summarize this portion of the talk, surges of EEG activity have been identified in humans around the time of death. Cardiac and respiratory arrest are associated with a surge of power, coherence, and directed connectivity. And some of these neurophysiologic features are associated with conscious processing, which I showed you at the beginning of the talk. Now, the story has evolved. I kind of stepped back to the work I was doing, but Jimo Borshigan published a follow-up article with Duan Li, who's in our group now. There have been other studies of the neural correlates of consciousness at near death. And also Stephen Lorry's group. Stephen Lorry's is a very, very accomplished and famous Belgian neurologist who's done foundational work in consciousness. His laboratory, others have looked at ways of trying to evoke near-death experiences in humans to understand those correlates. People have looked at psychedelic drugs such as dimethyltryptamine or DMT. People have been exploring endogenous DMT, including Dr. Borshigan and one of my former graduate students, the release of dimethyltryptamine, a potent psychedelic drug, during these near-death experiences. And one other aspect I wanted to bring up, which I think is quite interesting, is that there's a related phenomenon called terminal lucidity. And my father had this when he was dying in an ICU, and I witnessed this, and I didn't have a framework for it, but we were all just marveling at the fact that, wow, he's been delirious, and I was thinking he's been hypoxic. Now he seems like his old self. We took away the ventilatory support. He was dying, but he seemed like he came back. I noted this, but I didn't really have a framework until I started studying near-death experiences and realized that is a well-known phenomenon. And it also comes up with dementia. So people who have severe dementia, who are considered to have irreversible pathology, they're no longer communicating, etc., will oftentimes have these periods of intense lucidity right before they die. And I was part of a National Institute on Aging task force to consider this, because there are a lot of really interesting implications for the pathophysiology if, toward the end of life, the brain can somehow access the connections to start to meaningfully communicate and interact again. And this was a theoretical article that we put out. The NIA developed a funding mechanism for this. And I just think it's an interesting kind of cousin to the near-death experience. It's around the time of death. It prompts the question, what's going on with the neurobiology? What's going on at the network level that enables this to happen? Okay, so hopefully you recognize Andy Warhol, a pop cultural icon, who said, in the future, everyone will be famous for at least 15 minutes. And, this study had its 15 minutes of fame. It was covered by worldwide media because, of course, it's connecting to some bigger questions that we have about the border of life and death, about the border of science and religion, the border of the known and the unknown. Even as a small rat study was on the front page of the Washington Post right after it came out. So why was that the case? Well, I want to provide some other context, and I think it leads to some bigger questions and the kinds of questions that you might explore at your center, and I know that you have explored similar questions, and the relationship between religion and near-death experience. So as I noted, the near-death experience has been reported since antiquity, but it didn't really get into the popular consciousness, in the US at least, but elsewhere, until the 1970s, where Raymond Moody published a book called Life After Life. And there have been many books about the near-death experience, but they have primarily been in the realm of psychology and, still considered sort of fringe. I mean, consciousness science as a field is still fringe, but this is really on the fringe of the fringe, right? But in 2012, the year before we published these studies, there were 2 books that came out, not by psychologists, but by surgeons. And in fact, in one case, by a neurosurgeon, even Alexander, who actually at one point practiced at the Brigham in your neighborhood. He was in some type of comatose state, objectively, but experienced a profound near-death phenomenology. And he described it in this book, which he titled Proof of Heaven. Mary Neal was a spine surgeon who also had a profound near-death experience. She wrote a book called To Heaven and Back, and this resulted in this cover article in Newsweek, Heaven is Real. Now, there's so many questions here to unpack. I mean, and I think there are a couple that I want to focus on. Actually, one that I want to focus on in particular. There's something in the philosophy of mind referred to as the explanatory gap. This also comes up in the literature of consciousness sometimes as the hard problem of consciousness. And it breaks down like this. Even if you assume that you know everything there is to know about the brain, its neural function, how do you bridge the gap to phenomenology, to what we're experiencing, to our sense of perspective, to our interiority, to our experience, to our consciousness? What kind of article am I going to read that's going to make me say, oh, well, now I get it. Now I understand how this electrochemical activity turns into this world around me and the world around you right now that you're experiencing. And that explanatory gap happens even if you're talking about a completely healthy brain and 1 pixel of subjective experience. You're still faced with that gap. Well, now think about the near-death experience. You don't have a healthy brain. You have a brain that is dysfunctional, possibly, after a state of arrest or death. And you don't have 1 pixel of experience. You have the richest, most vibrant, most transformative experience of your life. Well, now that gap widens. And it widens so far to the point where some people say there is no relationship. There is no real bridge. There is no connection between the brain, or possibly no, I shouldn't say no connection, but rather the brain can't possibly generate conscious experience. Because if you can have this dysfunctional brain in a dying body, but on the other hand, have this rich phenomenology, then consciousness must be something different. It must come from somewhere different. And so, this and many other aspects related to, should we justify religious beliefs with science? If we do, what happens when the science changes? There are lots of questions to unpack here, but I just thought this was a particularly interesting one, this framework leading into the study that we conducted and some of the subsequent conversations. And there were lots of communications and comments that I received, some very negative, that, you haven't explained this, and negativity coming from the scientific perspective, also coming from the religious perspective. Other people felt validated. There are people who reached out who had near-death experiences who weren't believed, much as we used to have in our field with awareness during anesthesia, right? And there's some parallels to that as well. So they felt really validated, that yes, there's probably something going on in the brain here. So really, we could talk a long time about this, but just to wrap up, near-death experiences have been reported across cultures and have been argued sometimes as evidence that consciousness has a non-corporeal basis. Again, this widened explanatory gap that precludes any kind of bridge between the neurobiological and the phenomenological. Near-death experiences have been reported consistently in 10 to 20% of cardiac arrest patients. Think about that the next time you're at a code. Don't think about it during the code per se, but afterwards, could that person have been having a near-death experience? It's really wild to think about. right? And finally, in terms of the background story, electrical surges have been identified in the human brain just prior to death. And what we demonstrated in experimental studies is that neurophysiologic activity after cardiac and respiratory arrest, at least for a very transient period, appears to be organized and may relate to consciousness. I want to be very circumspect. I'm not saying this is the neural basis, but we do hypothesize that near-death experiences have some sort of quantifiable neuroscientific basis, even if we haven't necessarily shown it here. So I want to acknowledge my colleague, Dr. Borge again, who really was driving this, my colleagues Anshul Lee and Dinesh Pal. Anshul is a physicist, Dinesh is a neurobiologist. They were my postdoctoral mentees at the time. Now they're my collaborators. They're independently funded scientists. I want to thank all of my colleagues at the Center for Consciousness Science, my funding sources from the NIH. And finally, I would like to thank you again for the invitation to speak and for joining today to listen to what I had to say. Thank you very much, and I'll be happy to address any questions you might have. Thank you.
George, thank you so much. That is fascinating. And the way you tied things up and asked more questions at the end, right? So we're left with more questions. So that is really wonderful. I'm waiting for some of the comments and questions to come. We literally have 10 minutes to discuss. So if people have questions, please post it on the chat and we can ask George. There are several comments commenting about your talk, but I wanted to ask one question to lead off with. I know you are very fond of this feedback and feed forward work. And one thing that I wanted to ask is, how does the feedback inhibition leads to unconsciousness? You mentioned that, but how does it really take the next step of explanation?
Yeah, no, it's a great question. And look, this is one of many approaches, and I want to be humble. I think if I was giving this talk 8 years ago or 9 years ago when I thought, this was the key, I think it's informative. But, the wider dynamics that are going on and different dynamic states like criticality, there are lots of different things involved. But what I will say is, and this is independently of anesthesia, in the literature of consciousness, the reverberation, if you will, is thought to allow a sensory representation or stimulus that would otherwise rapidly decay to be sustained, to be amplified, and again, to become accessible to other cognitive processors across the brain. So it's sort of like, it's holding it up, it's keeping it going.
I see, okay.
And keeping it accessible. And when you lose that, and you just have this feed-forward mechanism, it's thought that, maybe you have sensory processing, but you don't have the kind of integration and sustainability of the representation to really experience it consciously. So that's the thinking. And if you block that, and there's also some computational things to support that, if you block that reverberant activity, that feedback connectivity, then you just lose that capability. I should also note that this is something that scales down even to Drosophila, the fruit fly. They don't have a prefrontal cortex, but they have these higher order nuclei and lower or more primary nuclei. And you see a feed-forward feedback phenomenon. And when you give them isoflurane, the feedback is suppressed. I mean, it's really, I was shocked. So that would be one answer.
The second aspect of this is, there are several, I grew up for 30 years in India, and always I heard about people talking, people really become more aware during death. And that is somewhat related to what you're talking about, the electrical surge. If I may ask, where was the electrical surge seen? Like, which part of the brain that you really actually saw that?
So this was using a BIS monitor. So it was going to be on the left side of the frontal cortex. Okay,
so we are not really sure more than that, right? Can't really zone into which
in humans, it was just electrical activity. I mean, they weren't measuring connectivity or coherence or anything like that. Bala, I see questions. Do you want
Yeah.
you want me to go through them, or are you gonna call them out?
You can, if you can go through them, that's fine. Yeah, I see a lot of questions here. Sorry.
Okay. Hi, is it correct to assume that near-death experiences can happen during non-threatening situations to someone who is under general anesthesia too? That says I am a lawyer.
So Shanti is a UNESCO faculty member. She's in Belgium. She's following us through our center. So yeah, go ahead.
Oh, wonderful. So I don't think there have been descriptions of near-death experiences. I mean, there might have been some sporadically, but having studied awareness during anesthesia and you know, looking at dreams during anesthesia, you don't tend to have that kind of vivid experience. I mean, out-of-body experiences are common. So I would say that there's some shared traits, but I suspect that they're different states. And I'm gonna, just because a shortage of time, I'm just gonna try to move on here. Somebody reported, you know, privately, so I don't want to say the name, that the husband had a near-death experience. It made, you know, a big impression, but didn't cause anxiety. And again, typically these are positive experiences. It's I think more infrequent that they're dysphoric, although that can happen. Shaz is asking, you know, clear memory trace of NDE created in situations where brain processes are presumed to work under diminished capacities. Any further implications? Yeah, no, that's a great question. So I didn't even talk about the memory piece, right? And I don't know, that really hasn't been studied. That's a great question, because again, some similar parallels. You're going to be taking care of patients in the operating room today who are conscious, even though you think general anesthesia is going on. I mean, it will likely be transient, and they will likely have no recall of it. So that needs to be studied, Shaz, you're correct. But also, it suggests, if we want to take the parallel, there are people who could be having near-death experiences that don't remember them, right? You know, it could be a higher proportion. So anyway, very interesting. So somebody asking about an EEG monitor during a code. Yeah, that's a great question. And I think I don't have a good answer for you. I mean, I thought about that more in the context of organ donation, you know, like really monitoring carefully, waiting until that activity is clearly quiescent.
The very least we could do is just to not have additional conversations which are irrelevant during that time, just in case people recall.
Yeah. I think there are some difficulties too, practically, as we, you know, we've all been to these codes, right? I mean, it's a madhouse, and you know, even thinking about like, can we get clear electrical signals? I guess if it was about to be called, we could pause, but I think that's very reasonable to consider. Oh, interesting. Can NDEs improve depression? So that's a fantastic question. I mean, I think as I stated, they really can be transformative, and I think one way to approach that, you know, I don't think we're definitely not going to induce death and hope they come back, but I think that it aligns with some of the work with psychedelic drugs, and you know, psychedelics are being aggressively explored for depression right now, and DMT evokes some of those aspects of a near-death experience. And it's important to note that it is thought, it's not clear, but it's thought that it's not just the presence of the drug in the brain, but rather the experience itself that has some sort of therapeutic effect. Okay, a question about visual and auditory pathways. Are persons without vision having the same circuits during consciousness and anesthesia? That's a great question, and I don't have a good answer for you, unfortunately. I don't know enough about that literature. Okay, so, you know, I think I'm going to take one more question. I really appreciate all these questions. It's fantastic. But the question Stephen has, if animals also have the same suppression of feedback connectivity under anesthesia, then are they conscious like us? So a couple months before that near-death study came out, I and Mike Alkire, who's an anesthesiologist, actually published another study in PNAS thinking about the evolution of consciousness and using the emergence from anesthesia to try to understand what is kind of the core primitive primordial requirement in humans to have a conscious experience. And there were some subcortical arousal centers, limited cortical activity, but some sort of, reverberant activity, some association cortex. And, then we sort of did some reverse engineering. Well, how far back do we need to go to find those basic neural correlates or that fundamental neural machinery? And it's really hundreds of millions of years ago in terms of a phylogenetic timeline. So are they conscious? I'd say yes. I personally believe animals, they have conscious experience. There's similar neurobiology. I think we know that, certainly when we're interacting with certain species. Are they conscious like us? That I don't know. I mean, I can't speak to the richness of the conscious experience. And that's where kind of the more elaborate connectivity, I think, comes into play in terms of the repertoire of brain states that we can access versus other species. But I think it's a really important question and something that needs to be pursued systematically. It's another good reason why we need a real consciousness monitor, which we don't have. Something that's principled, that's independent of behavior or language, independent of report, so we can see how conscious is a baby compared to us, how conscious is a dying person, how conscious is another animal, how conscious is somebody under a certain kind of anesthetic. So great question. Thank you for all the questions, but it's about 8 o'clock, and I know you all have important work to do, so I'll turn it back over to Bala.
George, thank you so much. I think this was one of the most well-attended lectures. About 130 people came for this. I know you talked about this as a fringe work, but I hope more and more people take this up and explore this a lot more, and hopefully this get accepted in the mainstream science and not just discarded. And a really lovely work, and thank you so much for all the work that you're doing, and hopefully we can collaborate in the future. And have a nice day, and thank you all. Yeah.
Thank you all. Have a great day. Take care.